trivalent categories. Okay, so we continue to consider categories that we can draw diagrams for. And the group we're thinking about today is something that I call trivalent, and this is going to be a little bit, theory isn't exactly the right word. There's going to be plenty of calculations, but for the examples, I'm going to tell you some things about examples, but then possibly not fill in very many details about those. I might do that tomorrow. So, okay, and what I'm talking about is mostly in a paper on the archive called Categories Generated by a Trivalent Vertex. This is a paper with Scott Morrison and myself and Noah here, who will be here next. Okay, so we start with the usual collection of adjectives. So when I say a trivalent category, I mean a tensor category in the sense of yesterday. So it's rigid, pivotal / planar. But in particular, I don't need the Karoubi condition today. So we don't require it to be Karoubi complete. Okay, well, if this was all, there wouldn't be any need for a new word. So of course, there's some more conditions. Oops, I underlined the wrong thing there. Okay, a trivalent category is a tensor category such that the category has a non-degenerate, when you take the bilinear form applied to x and y, you just take your two elements x and y and you connect all their strands together. So this is sort of like multiplication and trace from yesterday, okay? All the strands connected up. Now that is not the whole story.
I'm sorry, I'm a little confused because here. So what are I guess the number of strands is kind of arbitrary depending on x and y, or like?
Yeah, exactly.
Okay.
However many strands, x and y should have the same number of strands.
And what is a strand represent? Is it a generator, or what is this?
Yeah, we'll get there.
Okay.
So the objects are tensor generated by a single element, a simple, and we also require it to be self-dual generator that we call x. Okay, and so every strand here represents a copy of x, and we'll get to the rest of it. Well, this will make more sense after I finish writing these conditions down.
Oh, that x is different from.
Oh God, it's very different. This is a z. Yeah, thank you. Okay.
This not the generated form is with objects in C. It's not in vector space. So what it simply is like a puncture.
How about you ask me that same question again after I write down the third condition? No, because you're right that originally I didn't have this drawn in my notes, and then I said, well, that's silly. Why don't I just put it where it shows up for the first time? But now you're asking me very good questions that I realize will make more sense after I write down these other conditions. So, okay. So not only are our objects tensor generated by a single thing, our morphisms are diagrammatically generated by a trivalent vertex. Okay, so this is some map, and if I draw it like this, it's in, well, maybe for consistency, I'll draw it like this. So it takes in 3 copies of x and produces the unit. Okay, and with the way that I've drawn it, we're going to ask that it be rotationally symmetric. Okay, so Okay, so this means that if we start with our trivalent vertex and we pick up one of these strings and pull it around the outside so it lands on the other side, right? And that requires our pivotal structure to have this diagram make sense. Then this should be on the nose equal to the same thing if we hadn't done the rotation. Okay, so what this means is that, really if we're working in the diagram calculus for a pivotal category, we should have labels on strands, and we should have every morphism have some sort of coupon there with a box labeling it. But we are specifically zooming in on categories that are tensor generated by a single tensor generator. So we don't need labels on strands, and it's self-dual, so we don't even need to orient our strands. And because our trivalent vertex is rotationally symmetric, then really the objects that we're looking at, that's the wrong way to put it. The diagrams that we're looking at here can be treated like planar trivalent graphs, okay? So all of these conditions, so all the diagrams describing morphisms of C have the same data as planar trivalent graphs.
I have two questions.
Okay.
So the first question is, I seem to remember when dealing with a self-dual object with Fabrini Schur indicator -1, when I still needed to have some sort of way of orienting the strands.
So in fact, it's a consequence of these that it is symmetrically self-dual.
Okay, thank you. So that's the first. The second thing is, do we not need the little anchor star thing because we have that rotationally symmetric thing?
Yeah.
Okay,
exactly.
Cool, thank you.
Okay. And so now that I've asserted that when we're talking about morphisms in the category, we're actually talking about planar trivalent graphs, this non-degenerate form is taking as its input planar trivalent graphs, okay? And so you can make sense of taking two of those and putting them down for Z and Y and connecting up the edges as needed, I hope. Please, yeah.
So when you say that it's generated by, you mean under composition and things like that, but there's also morphisms you get for free, things like that.
Yeah, so when I say generated here, I mean that we already have the identity morphism on X, we have the cup and the cap, right, coming from our dual structure, so that in addition to that stuff we can kind of do to single strings, the only additional thing is a single flavor of trivalent vertex. Exactly, right? In order to draw this picture, I need to already have defined the, tensor with the unit, the, co-unit map, et cetera. Okay. Yeah.
I guess this is probably, I don't want to spoil the punchline, but I can think of one category.
Please don't.
Okay. I'll stop there. I'll ask the question. If the question still remains at the end, I'll ask it.
Yes, thank you. Okay. And there's more. So the fourth thing we're going to do, and we need some notation for this. If I write C with a subscript of n, I mean the Hom space going from X tensor n to my unit. Okay? And in order to call something a trivalent category, well, I'm actually going to summarize mostly things that I've already said, but then we're going to continue with this notation. So let's see. Oh, maybe this first one is something I haven't already said. That C0 is one-dimensional. Okay, in other words, so that's 0 tensor products of X, so that's the unit, right? So we're requiring that the unit be simple in this category. Dim C1 is 0, okay? And so this is saying that our generator X is not the unit itself. Okay, here's one I already said, right? That dim C2 is equal to 1. And that means that our generator X is simple. And C3 is also one-dimensional. And so the trivalent vertex is, this tells us that the trivalent vertex is unique up to scalars. Okay, but this is actually, we'll come back to that one in a minute, but this actually has more information in it than just that. Okay. Okay, and so of course, at this point, you're asking yourself why, right? Why look at categories with all these properties? That this seems really extremely restrictive, right? And of course, it is. And in another sense, when I get to some of the examples, you'll see that a lot of our friends, the sort of first categories we encounter, if we're studying tensor categories that are small in some sense, are trivalent categories. And so, okay, so the idea here is that we've really, especially at this stage, but even in its steps 2 and 3, imposed a notion of smallness on our category, okay, for some very non-technical meaning of small, right? But like tensor generated by a single thing, morphisms generated by a single trivalent vertex, and then a condition on these Hom spaces that they be small. Okay, and this seems like a weird way to think about categories, but on the other hand, sometimes if you think about categories in a weird way, you see things you might not see otherwise. Okay, so we're motivated by the classification of small index subfactors, where there's a notion of dimension, which is, so in that context, you also have a tensor generator X. And if you look at its Frobenius prone dimension and you insist that it be small, and you sort of gradually raise the bar on what you consider to be small, you see classical things. And then if you stretch just a little bit, you see the famous Hagerup subfactor, and then the Aseda Hagerup subfactor. And so we have the same idea here, which is that maybe we'll stumble on something interesting by taking a different point of view. And if the point of view that we take is that we're interested in small things, then at least we have some hope of doing the computations. Okay, so I guess the short answer here is we hope that being systematic about finding small categories may turn up something new. Okay. Okay, and before we get much farther, let's do an example. So the Temperley-Lieb algebra, sorry, the Temperley-Lieb category, right? We look at the even subcategory generated by the second Jones-Wenzel idempotent. Okay, we talked about these briefly last time, but in particular, the second one is very not bad. The second one is just the identity diagram minus the cup-cap diagram times 1 over quantum 2. Okay, so this is this kind of simplest Jones-Wenzel idempotent. And so now that's my object that's tensor generating. And my trivalent vertex is, so we conglomerate these 3 copies of F2. And then each one is joined to its neighbors by 1 strand. Good question here. Even is kind of a name we give this subcategory, just because if we're looking at F2 as our tensor generator, we have an even number of strands. Okay, so is this a good trivalent vertex? Well, sure. You pick one of these up and you rotate it around to the other side, and it's still the same picture you started with. Yeah. And what about all of these conditions? Well, the unit object is the empty diagram in temporally Lieb-Jones, so that's good. That F2 is simple is something, and not the identity is something we asserted yesterday. And now you'll have to take my word that this third space is one-dimensional also. And although it's not that hard to show, right? Sort of any diagram you draw that has 3 copies of F2 along the bottom, the Jones-Wenzel idempotents, recall, if you put a cap on them, they turn into exactly 0. So this is kind of our only choice of what to do with these strands to not have something get a cap put on. Okay.
Sorry, one more question.
Yeah.
Is this the full subcategory, or are you discarding some morphisms to get? I mean, because you have that one, the C3 space, which was one-dimensional. I assume if it hadn't been, you could have just reduced the size. But for other Hom spaces, are you kicking anything out, or?
Okay, remind me what full means here.
Whether or not you take all morphisms of the larger category.
No, we don't. Well, so if you like whatever you have from any morphism you have in your larger category, you just decorate its outside by sticking these Jones-Wenzel idempotents around it, and then if they turn it into 0, it's just 0.
Very dumb question.
Please.
What does trivalent mean in this context? Because you've drawn a picture where you have a trivalent vertex, but your picture there has no trivalent vertex. This one also has 3 strands which are unattached. This one now has 6. So okay. What
you really should think of is that I now use a different color chalk, and anytime I have, I've done this in the wrong order, a single orange strand, I say, aha, that's really 2 strands with a Jones-Wenzel idempotent on them. And anytime I have this, I replace it by, okay, I'm going to get lazy and stop labeling my Jones-Wenzel idempotents. So if you see a box, that's what it is. I replace it by this. Yeah, thank you. No, that's a really good question. What else?
Is this category fusion?
What's that?
Is this category fusion?
I don't think so,
okay. Because
in general, temporally Lieb will have infinitely many simple objects.
I see.
As long as your value of Q is greater than 1.
Okay.
And so here, you're only picking out the even ones, but you will still get all the even ones.
I see. Thank you.
And so, all right, let's continue this sidebar. When I say that we're interested in small categories, we've already listed out these dimension restrictions. But in fact, in terms of what we look at today, we're going to have some more. Okay, so we're going to zoom in on things where our C4 space is bounded by 4, C5 is bounded by 11, and C6 is bounded by 40. Okay, these are arbitrary. I don't expect them to make any sense to you at this point in the talk. Okay?
Excuse me, can you realize the maximum?
Sorry?
It's 4, 11, 4. Can you realize?
We will get to that. And I believe that, I think maybe I have a 4, 11, 39 example waiting in the wings. So, yeah. Okay. So, the principle at work here is that if one of these Hom spaces is small, then everything that follows that is bounded, okay? So this is small, that puts a bound on the size of the subsequent spaces. And this is best illustrated by an example, okay? So let's, like I said, dig into what this condition means. Okay, so
that's good. Does this example you gave satisfy those bounds or not? Or
this example?
Yes.
absolutely.
Okay.
Yes. These bounds, you mean? Yeah. Exercise to the audience.
Thank you.
Yep. Okay. So if Ci is small, that puts a bound on the remainder of these. Let's see what that means in the case of the one that we wrote into the axioms, that C3 is one-dimensional. Okay, so here is a planar trivalent graph, which has 3 boundary points. Okay, and so this is, well, I guess I should really pull one of these strings down like this. Okay, right? Because now this is a map from 3 copies of X into the unit, right? But we are starting with this trivalent vertex, and this space is one-dimensional, which means that this must be some multiple of the trivalent vertex. Okay, there's no room left, right? We have a one-dimensional space. We already have something that we know is in it. And so in fact, this is in the span of the trivalent vertex, meaning there exists a number t such that if I have a triangular face, I can just pop it, I can get rid of it, and I multiply by t. Okay, so this is like in Temperley-Lieb, when you have a closed circle, you throw it out, but you multiply by t. Here, we're allowed to throw away triangles, and when we do that, all we do is we multiply by some quantity t to remember that they were there. Okay, and so in any particular category, t will have some value. So we'll call this an exercise. What is t in this example? Okay. Now, let's skip that for a second and come back to that. So similar to the calculation that we did over there, showing that the triangle can be removed, if we have a bigon, okay, 2 trivalent vertices joined along 2 strands, then this is in the space C2. And so it must be some multiple of just the string by itself, and we'll call that multiple B. And if we have a closed loop of string, then we're way back in the space C0. And so this is just some number. And in analogy with Temperley-Lieb, we call this closed loop. Okay, and I'm going to label that as a piece of string. It's not a 0. Okay. And the one remaining thing we have is if we used a trivalent vertex like this and connected it with itself, then we would start with X and end with nothing with the unit. And so we'd be in the C1 space. And since this is 0-dimensional, this balloon is actually equal to 0. Okay, and so what we have here is that planar trivalent graphs represent the morphisms in this category. And we know that we have a relation between, if our diagram has any face in it, which is a triangle or a bigon or a 0-gon or a 1-gon, then there is some simpler diagram, which that is a multiple of, or maybe it's in the span of simpler diagrams. And so if we put a complexity measure on these planar trivalent graphs in terms of the number of faces they have, then we have these relations that simplify the graphs if any of those faces are triangle or something smaller. Okay, and so the rest of these relations come from our ability to look at graphs and get rid of small faces and enumerate what's left in some sense.
I have a quick question that might not be worth asking, but
Please.
is do we have a dagger structure or no dagger structure?
No, we don't
Okay,
have a dagger structure here.
thank you.
We are, in this paper, we work over the complex numbers, but in fact, we don't really make use of the complex structure. Most of this should work in some very similar form over an arbitrary field. Okay.
Sorry, just to see if I understood the comment about the bounds and the dimensions properly. You have some systematic way of generating planar graphs, and you do these simplifications and show there's basically for whatever c equals 4, there's like 4 cases that you can't reduce any further, and 11 cases for 5. And is that where the bounds come from?
Yes,
Okay.
pretty much. Okay, let's in fact do the C4 case now, just because we can. Okay, so here's a theorem that goes in exactly that direction. So we suppose that C4 is at most 4-dimensional. Okay, so then there exists a relation that lets us pop squares. Okay, there exists a relation that says that if we have a square, it can be replaced by some multiple of I, some multiple of H, some multiple of C, and some multiple of D. Okay, and I'm going to outline the proof not because this is challenging at all, but because it sort of gives you insight into the direction the rest of these proofs go in. So it sort of shows you the paradigm we're thinking in. Okay. So we consider D to be the diagrams with no faces among 4 boundary points. Okay. And so then we have a trichotomy, right? So either D is linearly independent, or D is linearly dependent, but I want to distinguish the sort of 2 different kinds of linear dependence you could see in this set. Okay, so it could have a relation of the form I is equal to some multiple of H plus some multiple of the cup and the cap and some multiple of the identity. And if you had a relation involving either the I or the H, this would be true, right? Because you could rotate everything by 90 degrees. And if you had a relation that didn't involve either I or H, then it would be something like saying that the cup cap is equal to some multiple of the straight up and down strands. Okay, and in all of these cases, we get the conclusion we want, right? Because if D is linearly independent, then we have a 4-dimensional space that it spans, and we've already required that this space be 4-dimensional, and so we're set. And now, if we didn't know that, right, if we didn't know that this set was linearly independent, then we could zoom in on the square, and we could apply a relation. Okay, so let's see. Let's circle a subpiece of this diagram, which looks like I. And now, in the interest of time, I'm not going to write out what would happen if you replace it with each of these. But if you replace it with this diagram or this diagram, well, okay. If you replace it with this, you end up getting a triangle, and we know that we can pop triangles. If you replace it with a cup and a cap, it's just an I diagram, and that's okay. That has no faces. And if you replace it with strands that go straight up and down, you end up with a bigone here, and we know that we can pop bygones. Okay?
You see here different from speed, am I right?
What is different from what? Oh, yes, sorry, this B is different from that B. Good point.
There's also two.
Oh, and there's two Ds. Okay, you know what? We'll just put primes on everything to be safe. Okay, excellent. So, okay, so we in condition case 2, we still have a square popping relation. And in the third case, we would draw our square and we would zoom in on this part in the middle here, which can be switched out for strands that go like this, and then we would have 2 bigons, and we can get rid of those. And so in fact, if we assume that C4 is at most 4-dimensional, then the meaningful graphs in our Helm spaces don't have any squares in them either, right? And so what that means is that when we look into C5, C6, C7, when we look further, we know that our space is spanned by graphs that have some maximum number of boundary points and no faces that are squares or triangles, bigons, balloons, zerogons, circles, whatever. Okay, and so having a dimension restriction here gives us some sort of restriction on the spaces that follow. And so I'm going to tell you about what we call the tree of life for trivalent categories. Okay, so this is the part where I'm going to write down a lot of examples without exactly telling you about them. Okay, and so let me see. So the very first branch that we get to is what happens with C4. Okay, so if C4 is 3 or smaller, we only have a few examples. We have, if C4 is equal to 2, then we must be looking at the Fibonacci category. Okay, recall that this, Dimitri defined this last week. This is a category with only 2 simple objects, 1 and x, and the relation that x tensor x is equal to 1 plus x. Okay, so kind of the smallest non-trivial category out there. Okay, and if C4 is 3-dimensional, then we have this category that we've already defined as the even part of the temporally Liouville-Jones category. Okay, also, this is also the quantum group category that comes from SO3. And now, the main trunk of my tree is going to be the statement that C4 is 4-dimensional. And over here is C4 that are greater than or equal to 5-dimensional. Okay, and so the story here is that just like climbing a tree, we just sort of grab the branches we can reach and we see where they take us. Okay, there's this whole unexplored portion over here that we can't say anything about. And that's not to say it's not interesting. Okay, it's just that we've created a paradigm for ourselves where we can say something about the things that come up on the left side of the tree. And there's not anything we can say about what comes up on the right side of the tree. Using this sort of systematic techniques, right? Certainly there's stuff over here that we know about, but we don't have it organized according to this way of thinking. Okay, so if C4 is 4-dimensional, then of course we would look at C5 next. And this next branch where we can actually say something specifically, C5 is less than or equal to 10. The main trunk of the tree is C5 equals 11, and if C5 is 12-dimensional or higher, we throw up our hands in despair. Okay, and what do we see over here? We see, okay, so if this C5 is 9-dimensional, we see the quantum group category for G2 at a generic root of unity. And now with the 9-dimensional restriction, if Q is a 10th root of unity, we get G2 there. And we also get something we call the ABA category, which if I have time, I'm happy to tell you what that is. But for now, let me just say that this is a subcategory of the free product of TLJ and the Fibonacci category. Okay, and now we can climb one more step up this tree. Okay, and so let's think about C6. So if C6 is less than or equal to 40 dimensions, then we find the H3 category. Okay, so this category is Morita equivalent to the Hagerup fusion categories. Okay, so this is due to Pinhas-Grossman and Noah Snyder, the discovery of this category. And so it's interesting to have it pop up in this tree, right? Because we go out looking for small things, and if we do that in the subfactor world, we find Hagerup, and if we do that in the trivalent category world, we still find Hagerup wearing a different hat. So, of course, a second or third or fourth appearance of a mysterious thing is less exciting than the first, but it is still fun to see it here. Okay, and then here is those things where C6 is greater than or equal to 41. Okay, and why did we stop where we stopped? Well, a lot of the work here is done by computers. It amounts to writing down a giant matrix of diagrams and evaluating those diagrams using these relations as much as possible and taking some huge determinant. And we sort of hit the point where the computer couldn't answer these questions in less than a few hours and stopped. Okay, so someone who knows more than I do about computer programming might not find it so challenging to extend this tree a little further. But certainly you would need to have a new idea if you want to make something other than incremental progress here. Daniel, do you have a question?
I do have a couple questions. So one is Fib the only, because you said, I was thinking, the initial question I was thinking is like, Fib seemed to be the only fusion category to me that you're going to get this way, but then it seems like there might be other fusion category. It seemed like it was going to be the only fusion category you're going to get this way.
Okay.
But then it seems like there's other fusion categories, and that kind of surprised. So is there the other fusion categories you can get this way besides Fib?
Are there other fusion categories?
Because initially, when you wrote down the definition, I thought Fib was going to be. It seemed like that uniquely forced to be Fib, but it's not. There's not. So something. Oh, because I guess I'm thinking that like you can have sub objects appearing later, and that's how. Because the strand isn't doesn't have to be the only non-identity simple object, right?
Maybe we should talk about this later. Okay. I'm not totally sure.
Okay, I guess, yeah, sure. And then the other question is, where's the Hagerup-Peters or extended Hagerup?
Somewhere up here.
Okay.
Right. So, given a general fusion category, I'm not actually confident that I can quickly tell you whether it is a trivalent category or not. So I'm not even going to swear that those other exotic fusion categories live in this framework. But yeah. Okay. So yeah, let me tell you a little bit about the technique of these proofs, right? Not exactly all the details, but okay. So the technique here is that we start with collection of diagrams, call it D, in specifically one of these spaces. Okay, so for example, we might take the 10 diagrams with 5 boundary points and no internal faces inside C5. right? So these are easy enough to describe. You can have either a single trivalent vertex and an unconnected loop of string. You could have all 5 rotations of this. Or you could have a trivalent vertex and then, oh no, I made that 4-valent. Try that again. Trivalent vertex and another trivalent vertex and a third one with 1, 2, 3, 4, 5 strings around the side. So also in those rotations. Okay. And so given this collection of diagrams, chosen in some way, I don't want to say to be clever, because you don't have to be particularly clever to decide to look at these, but chosen in some strategic way. Okay, so, you know, we think of the complexity of these diagrams as coming from the number of faces. And so choose things with, you know, no faces or a small number of faces to be the set that you're considering. Given this collection of diagrams D, then one of the following 3 things is true. Right, so it could be that D is linearly dependent. Okay, and we detect this by looking at the determinant of the matrix that we get from the form, which at the beginning, remember, we asserted that this was non-degenerate. Okay, that we were working in a category that had a non-degenerate form. And so we look at the determinant of this indexed over diagrams in D. And if this determinant is equal to 0, then the set D is linearly dependent. And there's a relation among. Okay, and so having that relation will enable us to come up with some sort of algorithm for simplifying diagrams. Okay. Now the next possibility is that D is a spanning set for C. So there's not a relation among these diagrams, but any other diagram you have can be written down as a collection of the diagrams in D. Okay, and the third possibility is that D is linearly independent and it doesn't span. And so this tells me that the dimension of Cn is bigger than the size of the set D. Okay, and so that's what's happening at each of these triple branch points over here. Okay, so, you know, with C4, right, if we had the linear independence of these 4 diagrams, but we knew that that was it, we'd be on sort of the main trunk of the tree. If we had a relation among them, then enough bits in the space collapse that we're actually out on this branch. And if we have that these diagrams are linearly independent and they don't span the space, then we're out here in these unknowns. Okay, so that's what these triple points are up to this point where we can't really say anything beyond this step. Okay.
How'd you come up with these numbers? So why 4 or 10?
Sure. So 4 is because there are 4 of these diagrams here without any internal faces, once you've already forbidden triangles and smaller things. 10 is because there are 10 of these diagrams here without internal faces, once you've forbidden squares and smaller things. And so I believe that 40, now, okay, things get, you're sort of already kind of at the edge of what you can deal with out here. So I don't swear to you that 40 is the number of diagrams you can get without any pentagon or smaller faces, but it's something like that. Yeah. Yeah.
So I have so you spread the branch. You allowed to consider 11 though, but you said there are they're just 10 5 ones with no faces, right? So there's something that you were able to deal with it then, I guess. Like there's like, I don't know, the fact that like with the 4, it's like, okay, there's no small places you put the branch, but then here, I don't know if I'm big, but there's like, it seems.
So in fact, at this branch point here, we have that we have 10 of these diagrams with no internal faces. And so, this should have said dim C5 equals 10, not equals 1. Much better like that.
I thought you were saying there was 11. Because you have 11 up there.
No, you're right. That's 11. Okay. And so in this case, we add on a single pentagon to this set, right? And so what that means is that we cannot pop a pentagon when it appears, but there are some further relations involving pentagons that we can say something about. So here we're allowed to have pentagons that show up, and then I think this relation arises from saying that if you have 2 pentagons next to each other, you can say something about that particular diagram, which has 6 boundary points.
I see. Thank you.
Yeah. What's happening here is that we're sort of running into the edges of what the Euler characteristic can do for us, right? So we're talking about planar trivalent graphs. So it's a theorem that any planar trivalent graph with no exterior boundary points has some small face, right? And by small face, we mean anything that's a pentagon or smaller. Now, once we're allowed to have points around the boundary, the statement turns into something much messier, more like if we have, a bound on the number of points along the boundary and a sufficient number of faces on the inside, then we can still conclude that there's a pentagon there, but it's a little trickier. Yeah, and so that is why this stops here. And I don't think that I need to tell you any more of the details of that. So I am certainly planning to talk about the Hagerup categories tomorrow or on Friday. And so maybe, yeah, I think this is a good stopping point for today. So.
Yes, thank you very much. Is there questions?
Okay, my question is for all of the ones that are on the known side, are you able to evaluate all closed diagrams?
Certainly we can evaluate all closed diagrams because that is a statement about C0, right? A closed diagram has nothing.
I guess the point is, do you have an algorithm to like, because like, or like, I guess you can put it to a number, but not always, but like, you have like a way of like, you can like, given anything, you can like figure out, if you give you a set, can you figure out? I don't necessarily
have a nice algorithm, but yes, I could do it. I have a computer program somewhere that has these relations actually written down.
Okay, thank you.
So it's just a question of going through and being like, a pentagon, let's replace that with this weighted sum of 39 other things.
Sure.
Could you just remind me the meaning of Morita equivalence here? Just you forget the tensor structure?
Okay, so yeah, this is a good question. So to a subfactor person, Morita equivalence just means that there is a subfactor that has this as one of its even parts, and the Hagerup category is the other one of its even parts. But let me see if I can translate that into fusion categories. I think that it means that we should have, so this is Morita equivalence. A fusion category C is Morita equivalent to D if there exists a bimodule category M, okay, with one action of C and one action of D, such that if we combine it in one order, we get C, And if we combine it in the other order, we get D.
Okay, thank you.
Any other questions?
Do you know something about finiteness of all dimension on the right side of U3? Do you have
Finiteness of,
yeah, existence of a
no.
series where you have infinite thing?
Well, what do you mean by infinite?
Some dimension of Cn with big N.
You're saying that in fact, there's no reason to expect that these should be
That's a question.
finite numbers at all. Yeah, no, that's a very good question.
Either
But
you exist or find a counter example.
I do not know.
Okay, if there are no more questions, then let's thank Maria again.